All right. Well, welcome to all of our participants to the 5th session of our U.S. Territories Water Operator Training Series. Today we'll be going over the Safe Drinking Water Act and talking about the drinking water regulations established within. My name is Michelle Olson. I am a water utility trainer and specialist with the Southwest Environmental Finance Center here in Albuquerque, New Mexico. I've been with the Southwest EFC since the beginning of this year. Before that, I worked for the state of New Mexico for over a decade. I worked in the Drinking Water Quality Bureau, implementing the Safe Drinking Water Act for almost 4 years, the Office of the State Engineer doing Water Rights Administration for almost 6 years, and before that, the Air Quality Bureau working with the Clean Air Act for 2 years. The Southwest Environmental Finance Center operates out of the University of New Mexico School of Engineering, and this training series is funded by the U.S. Environmental Protection Agency. Before we begin, I'll let you take a moment to locate your control bar and just do a quick review. So the button labeled audio on the far left is for muting and unmuting yourself. Make sure you remain muted during the webinar. You can unmute yourself if you want to ask a question or if you have something to contribute to the discussion. You could also use the chat function to ask questions. So if you post anything in the chat, make sure you send it to everyone or to my colleague, Matt Ziegler, who's helping to facilitate this training. So don't send anything directly to me because I won't be checking the chat as I'm presenting. And if you need to leave the training early, go ahead and use the leave button on the far right. Our U.S. Territories Water Operator Training Series is 26 sessions total, 1 hour each, and the trainers will vary depending on the topic. This is the schedule for the remainder of this year, 2025. So our next session will be Wednesday, September 3rd, where we're going to be going over source water characteristics. And I believe Tucker Colvin will be the trainer for that session. Recordings of our sessions and copies of the material are available on our website, and we will be posting the link in the chat. Okay, so I am going to turn off my camera. And without further ado, I want to introduce you to the Safe Drinking Water Act, also referred to as SDWA. So what is SDWA, the Safe Drinking Water Act? It is the primary federal law that regulates and monitors drinking water quality in the United States. It tells us how we have to treat our water and what contaminants we have to monitor for and how often we have to monitor for them. It's up to EPA to implement and enforce these standards with U.S. territories, states, tribes, local suppliers, and localities. The purpose of SDWA is to make sure that our consumers are getting safe drinking water, and it protects our consumers from naturally occurring and human-made contaminants that could be found in the drinking water. The history of SDWA. SDWA went into effect on December 16, 1974, and it requires EPA to establish national primary drinking water regulations for contaminants that may cause adverse public health effects. It's EPA's responsibility to continually assess these regulations and determine if they need to be modified or if new regulations need to be added as we learn more about contaminants that affect public health. This is to ensure that the Safe Drinking Water Act continues to protect us. For example, when SDWA went into effect in 1974, we didn't know that when chlorine is added to water, it combines with precursors to form disinfection byproducts, or DBPs. So DBPs have adverse health effects, especially with long-term exposure. In 1979, we learned that DBPs such as trihalomethanes, or THMs, cause diseases like cancer, and standards were later implemented. A number of safe drinking water amendments happened in 1986. In 1989, the first total coliform rule and the surface water treatment rule went into effect. In 1993, there was a big outbreak of cryptosporidium in Milwaukee, Wisconsin that made over 400,000 people sick, and it resulted in at least 69 deaths. It's the largest documented waterborne disease outbreak in the United States history, and it caused a flurry of new regulations and amendments to the Safe Drinking Water Act. In 1969, the surface water systems had to start filtering and treating their water more thoroughly because of that crypto outbreak. In 1998, we had the interim enhanced surface water treatment rule. 2001, we had our filter backwash and recycling rule. 2002, the long-term 1 and enhanced surface water treatment rule. In 2003, the stage 2 disinfection byproducts rule came around, along with more surface water treatment rules. The groundwater rule, which affects most of our systems today, was implemented in December of 2009. This requires systems to monitor their sources to ensure there aren't E. coli bacteria in those sources. It also requires that sanitary surveys have to be completed to look for sanitary defects that could allow contamination to enter your water. The total coliform rule was revised in April of 2016 and requires a number of additional steps that need to be taken if your systems had a recent contamination. I'm sure you all know last year in January, the revised lead and copper rule came around that requires you to look for lead service lines in your system. And at the end of the year, the lead and copper rule improvements came out. Most recently, we're having to test for PFAS, those forever chemicals, which have transitioned from monitoring under the Unregulated Contaminant Monitoring Rule, or UCMR, to having enforceable limits under the National Primary Drinking Water Regulations. The Safe Drinking Water Act also defines what a public water system is. It establishes regulatory programs with the state and with the federal government. It establishes both national primary drinking water regulations as well as secondary drinking water regulations. It requires that you communicate with your consumers to let them know the quality of their water. It also outlines preventative approaches to delivering safe drinking water. It lets you know what you can do to protect your consumers from contaminants in the drinking water. So SDWA applies to every public water system in the United States. What is the definition of a public water system? So this is a question that comes up all the time. You might see it on an operator certification exam. It's also something that you should be aware of because maybe a non-public water system crosses that threshold and becomes public. Now they have to follow the Safe Drinking Water Act regulations. So a public water system serves 25 or more people for at least 60 days out of the year. Or it provides water to at least 15 service connections. So you can have one service connection that provides water to 25 or more people, or maybe it's just you and your family in a town. It's just the 4 of you, but you've got 15 buildings in it, each with their own service connection. So that's also considered a public water system. It's one or the other. And based on the population you serve, you're going to have different public water system types. Community water systems. Community water systems are our most regulated water systems, and that's because they provide water to at least 15 service connections used by year-round residents or regularly serve at least 25 year-round residents. Those people are in contact with that water every day, washing, bathing, cooking, and drinking. So those are our community water systems, year-round, at least 25 residents. Then there are 2 non-community water systems. The non-transient, non-community water systems serve at least 15 service connections or 25 of the same people for at least 6 months in the year. They serve the same people even though they aren't residents, so they don't live there. But maybe they work there or maybe they go to school there. So they're in contact with that water day in and day out for at least 6 months in the year. The other non-community water systems out there are our little ones, the transient non-community water systems. So these water systems serve at least 15 service connections or 25 people that aren't the same individuals. That transient population that comes and goes. 25 of not the same people at least 60 days of the year. So you have a campground. There are a couple of employees that staff the campground. Those are the non-transient portion of the population, but there's less than 25 of them. Then we have our campers that come and go throughout the year. They make up the transient portion of the population, and there's more than 25 of them. So these are our least regulated systems. What are the different Safe Drinking Water Act regulatory programs? Again, it's EPA's responsibility to both implement and enforce these programs, but they do grant primacy to implement and enforce SDWA to our states, as well as to the Navajo Nation. So the Navajo Nation is the only tribal nation that has primacy to regulate and enforce the Safe Drinking Water Act. Now, if you went ahead and counted up all of those states, you'd notice there's only 49. One is missing. So do you know which one is missing? EPA has to do direct implementation, meaning they have to directly regulate and enforce the Safe Drinking Water Act with federal facilities like the Pentagon. So the Pentagon has its own water system. This is our missing state. If anybody knows which state that is, it's actually Wyoming. Wyoming does not have primacy for the Safe Drinking Water Act. Instead, EPA does direct implementation with Wyoming. EPA does implementation with federal campgrounds and in the national forest. On airplanes, airplanes can be considered a public water system. With our tribal nations, that's a direct federal government to sovereign nation government relationship. For example, my state, New Mexico, cannot regulate and enforce the Safe Drinking Water Act with our tribal nations. EPA has that responsibility. And with the US territories. So that's American Samoa right there. So one of the things we're going to look at today is how EPA implements the Safe Drinking Water Act with your systems. Drinking water regulations are split into two parts. The first part is the National Primary Drinking Water Regulations. These are health-based standards. These are the contaminants that we have to sample for and make sure we're in compliance with. The second part are the National Secondary Drinking Water Regulations. So these are aesthetic-based standards. Maybe your water doesn't look good, or it has some color issues. Maybe it smells bad. Maybe it tastes bad. So these are things that will make people complain and not want to drink the water, but they don't cause health effects. Those are secondary standards. This is what the National Primary Drinking Water Regulations look like. When we look at the National Primary Drinking Water Regulations, we can see which contaminant is regulated here in the left column. We can see what the maximum contaminant level or MCL allowed is, or if there's a treatment technique we need to use to ensure public health. The regs also tell us any potential health effects from long-term exposures and where sources of contaminants come from. And you'll notice here in the last column, there's a public health goal. So for Alicor, the public health goal is 0, but over here, the MCL is 0.002. So you might ask, why isn't the MCL the same as the public health goal? Well, the public health goal is a goal that says that at this level, there won't be any health effects. Any level of Alicor in your water is going to cause health effects, but the MCL is set a little higher for a number of reasons. Some of it has to do with cost benefit. So how much does it cost our water systems to treat the water to make it safe? Sometimes if it costs a ton of money and that's too much for our small systems to bear, they may set that MCL a little higher than the goal. Other times it has to do with laboratory procedures. So our lab procedures can't measure down to 0. There's non-detect, which is a level so low the labs can't detect anything, but we don't have any laboratory procedures that allow us to measure to a concentration of 0. So we have to set the MCL a little higher based on what our detection limits are for our labs. Maximum contaminant levels are one way to make sure we're in compliance. The other way to ensure we're in compliance is by using treatment techniques. Treatment techniques in the Safe Drinking Water Act are set if it's not economically or technologically feasible to determine the level of a certain contaminant. These are enforceable procedures that you have to use to treat your water. This ensures that it's safe to consume and meets the levels set by the Safe Drinking Water Act. Some examples of treatment techniques are with surface water and filtration. With surface water, you're going to have a bunch of suspended solids in it. You're also going to have bugs like Cryptosporidium and Giardia. So the treatment technique for surface water is filtering that water. If you filter your water, if you remove turbidity down to a certain level, like 1 NTU or less, then you know you're getting rid of all of the bugs in the water. Another example of a treatment technique is if you have corrosive water and you're exceeding action levels for lead and copper. So you may have to add chemicals to your system to make it less corrosive. Adding chemicals like orthophosphate, or in this case, sodium silicate, which are corrosion inhibitors, stop lead and copper from being leached out of your plumbing and into the drinking water. Another treatment technique example, the revised total coliform rule says we must complete a level 1 assessment after having more than one coliform present sample in your distribution system. The national primary drinking water regs include the groundwater rule. We've talked a little bit about that, which requires you to sample your water sources as well as do sanitary surveys in your system. These other rules are for surface water systems. So if you have a surface water system, you have to know about the filter backwash recycling rules, the long-term 1 and 2 enhanced surface water treatment rules. The chemical contaminant rule, the radionuclide rule, the arsenic rule, PFAS are currently regulated under the National Primary Drinking Water Regulations. Right now, the EPA has set MCLs for 6 PFAS in drinking water, and systems are undergoing their initial testing. The distribution contaminants that are part of the regs are the revised total coliform rule, the disinfectants and disinfection byproducts rule, and the lead and copper rule. So it's up to you to know these rules and how they affect your system. If you're taking an operator certification exam, you should know all of the rules because they may come up as questions on the exam, whether they apply to your specific system or not. So those are the primary drinking water regs. Here are the national secondary drinking water regs. You can see it's not a huge list. So our secondary regs are not enforceable by EPA. They're going to have aesthetic effects. They'll make people not want to drink the water. They could be color or odor issues. They could be total dissolved solids like hardness or salt that may be in your water. Again, these are all non-enforceable by EPA. How your specific water system has to monitor for the different contaminants listed in the regs is based on a few different factors. So first, your monitoring schedule will depend on the type of system you have. Community water systems have the most stringent monitoring requirements. That's because the same people are using that water all year long, so the water has to be safe for consumption at all times. Non-transient, non-community water systems can have monitoring schedules that reflect their operating schedules. For example, as we'll talk about later, you can't collect lead and copper samples during the summer at a school that's closed for summer break. You have to collect during times of regular operation. Finally, our transient, non-community water systems tend to have monitoring schedules that reflect their transient nature. These systems only have to test for contaminants that cause acute health effects, the ones that can make you sick with one exposure, because a transient population isn't going to be consuming that water long enough to experience chronic effects. Water source type. Are you a groundwater system? Do you get your water from a well? So these systems are subject to the requirements under the groundwater rule. Are you a surface water system? Do you get your water from a river or reservoir? These systems are subject to the requirements under the surface water treatment rule. GUDI systems are groundwater under the direct influence of surface water. Those have different monitoring requirements. Treatment type. Some treatment processes can reduce your monitoring requirements. Under the surface water treatment rule, a system using unfiltered surface water has to monitor for cryptosporidium more frequently than systems using membrane filtration. Some treatment processes can lead to an increased monitoring schedule. For example, certain systems that use chlorine to disinfect also have to test for disinfection byproducts. Finally, your system's historical water quality results impact your monitoring schedule. When a water system first starts up, you're required to take a lot of water samples. You have to test for things like VOCs, SOCs, radionuclides, nitrate, nitrite, DBPs, lead and copper, etc. So you have to sample for these under what is called a standard monitoring schedule. So this is the baseline monitoring frequency required for a contaminant. If the sample results are found to be below a certain threshold, and this varies for each contaminant, you may be placed on a reduced monitoring schedule, which is a less frequent monitoring schedule that's allowed as long as you can demonstrate consistent compliance. Here are a few examples of monitoring schedules. This first one was generated by EPA from the SDWA database. The second one is generated by EPA from the DME database. And this third one is from the New Mexico Environment Department. So they publish everybody's sample schedules on a website called Drinking Water Watch instead of sending them out individually. So you can see they all look a little different, but they all tell us the same information. They tell us what contaminant is being monitored for, the sample point where the samples need to be collected, the frequency of collection. Sometimes they tell you when the next sample needs to be collected. So there's a lot of information, but you get the idea. And your sample schedules may look different from these, but it's important that you review them every year so you can plan what you need to collect in advance to ensure that you're in compliance. SDWA also tells us where we need to collect our samples. Some samples need to be collected at the source. Source water samples are collected before any treatment, from raw water from wells, rivers, and reservoirs. Other samples need to be collected at entry points to the distribution system. These samples are collected after treatment, but before entering distribution pipes. Finally, some of these samples need to be collected in distribution. These samples are collected from distribution pipes, or in the case of lead and copper, at the tap, after water enters the distribution network. So first we'll talk about source water monitoring. These are our raw water samples collected before any treatment. So source water monitoring identifies contaminants that could challenge treatment processes. The groundwater rule requires source water monitoring. The primary purpose of the groundwater rule is to prevent waterborne illnesses caused by fecal contamination from bacteria. The groundwater rule requires that sanitary surveys be conducted on every public water system every 3 to 5 years. So once every 3 years for community water systems and once every 5 years for non-community water systems. And this is to inspect for contaminant risks such as cracked wall casings. The groundwater rule also requires triggered monitoring of public water systems to detect fecal contamination. So triggered monitoring is testing that is initiated in response to a specific risk event that suggests that fecal contamination may have occurred. For example, if a routine total coliform or E. coli sample collected in distribution comes back as present, samples must be collected directly from all wells or sources that were in use at the time of the hit. So these are raw water samples. The surface water treatment rule is another rule that requires source water sampling. And the primary purpose of the surface water treatment rule is to protect public health by reducing waterborne disease caused by microbial pathogens in systems that use surface water or groundwater under the direct influence of surface water, those GUDI systems. This rule requires these systems to filter water unless they meet strict criteria for avoiding filtration, which is rare. Like the groundwater rule, the surface water treatment rule requires sanitary surveys be conducted every 3 to 5 years. But in this case, it's once every 3 years for unfiltered systems, which again are rare, and once every 5 years for filtered water systems. This is in order to evaluate watershed controls, infrastructure, and operational practices. The surface water treatment rule also sets disinfection requirements. You can use filtration to remove protozoans and viruses. You could also use chemical disinfectants, which like chlorine, chloramine, ozone, and UV. Requires that systems test source water for cryptosporidium. If you remember that 1993 Milwaukee cryptosporidium outbreak we talked about. It also sets turbidity standards. So turbidity is a measure of water cloudiness caused by suspended particles like silt, clay, algae, microbes, which can affect water quality and safety. So turbidity can harbor microbes by giving them a place to hide. It can protect pathogens from exposure to UV light or chlorine. And sediment can bind to heavy metals like lead and mercury or pesticides, which will increase toxicity. So because of these problems, turbidity has a regulatory limit that is measured in nephelometric turbidity units, or NTUs. The higher the value, the dirtier the water looks. Filtered systems, which are most of our systems, must maintain a turbidity of less than 0.3 NTUs, 95% or more, in 95% or more of your monthly samples, with a maximum turbidity of 1 NTU at any time. So you can't go over 1 NTU. Unfiltered systems, again, these are rare, but they have stricter requirements, such as continuous turbidity monitoring. Okay, entry point monitoring. These are samples collected after treatment, but before entering distribution pipes. Samples collected at these locations verify treatment effectiveness and compliance with MCLs. The chemical and radionuclide rules, which are monitored at entry points, are in place to protect public health from naturally occurring and human-made chemicals that are known to cause long-term health effects, like cancer and organ damage, even at really low concentrations. So water sampled at entry points is representative of the water that we serve to our customers, and so it's monitored before public consumption. Nitrates and nitrites come from septic systems, animal waste, and fertilizer, and they can cause blue baby syndrome, which is where a baby's skin appears blue or purple because of insufficient oxygen in the blood. So this most commonly occurs in babies under 12 months, and it can be life-threatening. This is an acute health effect, meaning it only takes one exposure to make babies sick. The rest of the contaminants we're going to talk about under these rules cause chronic health effects, meaning it takes long-term exposure to get people sick. IOCs come from naturally occurring sources as well as human-made sources such as refineries and factories. VOCs come from industrial chemical factories, petroleum factories, herbicides, pesticides, etc. So IOCs and VOCs can cause cancer, nervous system and organ damage, and reproductive problems. SOCs are linked to hormonal and reproductive issues, cancer, and immune dysfunction. Radionuclides come from both naturally occurring and human-made sources and are associated with cancer. And PFAS come from discharge from manufacturing and industrial chemical facilities, certain firefighting activities, and the use of certain consumer products like nonstick cookware, water-resistant and stain-resistant fabrics, fast food wrappers, cosmetics, dental floss. PFAS don't break down naturally in the environment, so they stay in your body and in the environment for a long time, like thousands of years, hence the name forever chemicals. They have developmental, cardiovascular, immune, thyroid, and liver effects, and they're also associated with cancer. So the MCLs for these substances are listed in the regs, and EPA will let you know your monitoring schedule for these contaminants based on the factors we talked about earlier. Okay, finally, our distribution samples. These are samples collected from pipes or taps after water enters the distribution network. Samples collected and distribution detect contamination from pipes or stagnation, and they ensure safe water in the distribution system. The rules that require distribution monitoring are the revised total coliform rule, the disinfectants and disinfections byproduct rule, and the lead and copper rule. The first distribution system monitoring rule we'll talk about is the revised total coliform rule, or the RTCR. The aim of the RTCR is to protect public health by monitoring and reducing microbial contamination in drinking water. What types of systems have to comply with the revised total coliform rule? Well, all of our public water systems are community, non-transient non-community, and transient non-community water systems. What are total coliforms? Coliforms are a type of bacteria that are common in soil, plants, and the intestinal tract of warm-blooded animals. Total coliform is a broad group of coliform bacteria whose presence may or may not indicate fecal contamination. Fecal coliform are a subgroup of coliform that come primarily from the intestinal tracts of warm-blooded animals. E. coli is a subset of fecal coliform, so E. coli can cause illness. Coliforms are mostly non-pathogenic bacteria, Pathogens are disease-causing organisms, so non-pathogenic organisms are the ones that don't make us sick. Well, why do we bother to test for coliform if most of them don't make us sick? While coliform themselves don't cause disease, there are a lot of organisms that do, and they shouldn't be in our water. If coliforms have found their way into our water, there's a risk that other more harmful pathogens could also be present. There are 3 categories of waterborne pathogens that we're concerned about. The first are protozoans, which are these little one-celled animals like Cryptosporidium and Giardia. We don't want them in our water because they make us very sick and they're hard to get rid of. So if you see this picture of the Cryptosporidium, it's like this little worm and it has a cyst around it. And that cyst is really hard to penetrate. It's highly resistant to chlorine. Instead, these guys need to be removed by filtration or exposure to UV. And ingesting just a few of these cysts can make you sick. Next are bacteria. These are single-celled microorganisms. They're smaller than our protozoans. They cause a number of diseases, including typhoid fever, dysentery, Legionnaire's disease, and cholera. I don't know if you've heard, there's a huge cholera outbreak in the Sudan right now. So they grow really quickly in warm water, especially warm stagnant water. Finally, we have our viruses. These are ultra microscopic infectious agents. They're smaller than our bacteria, and they're not even really considered to be alive. They're just these little packets of genetic material that replicate themselves inside of a host. Waterborne viruses, such as hepatitis A, rotavirus, and norovirus, cause serious illness. All of these pathogens cause acute public health effects, so it only takes one exposure to make you sick. And we can't test for all of these pathogens out there. It's too hard and it's too expensive. But coliform are quick and they're easy to culture, so we use them as an indicator that disease-causing pathogens may be present. I think of coliform presence as that check engine warning light that sometimes pops up on your dashboard. You know, it lets you know that something's wrong with your system that needs to be taken care of immediately. How do these pathogens get into our drinking water in the first place? Well, they can come in through a number of different sources. So here is a drinking water well, and it's in a pit. And you can see from these mud cracks on the ground that that pit floods. You can also see these little openings at the top of the well where contamination could enter when it floods. This is a surface water treatment plant that's not filtering effectively, so it's letting contaminants into the system. Pathogens could get in through leaks and breaks in your distribution system, and they could get in through our storage tanks. So this is a storage tank that used to have a roof on it until a bear fell through and contaminated the water. Knowing how pathogens get into our system is important, so you want to make sure to check and resolve any issues that come up before they become a problem in order to protect consumers from contamination. RTCR monitoring. So these are our routine samples. The number of samples a water system has to collect is based on the size of the population served. The more people, the more samples that need to be collected. So as I mentioned, I live in Albuquerque, New Mexico, and we have a population of just over 500,000. 560,000. That means our water system has to collect 210 water samples a month. These routine samples have to be collected monthly in distribution at representative sites. There are no exemptions, and you have to rotate through the sites. Sampling is also done by the water system, so you want to be sure to follow your sample plan. The method used to test for coliform and E. coli is called the ColAlert, or MMO-MUG. So this test gives fast results within 24 hours. Here's a series of samples that have been incubated for 24 hours, and we can see that this one has turned really yellow. So what the lab does is it puts all the samples next to a comparer. A comparer is a bottle that's provided by the company that indicates what color the sample will turn if it's TC present. So they're going to compare your sample to that bottle. And if it's yellow or more yellow than the comparer, then we have a coliform present result. Then what they're going to do is they're going to take those coliform bottles and they're going to put them under a black light. And if they glow as much as the comparer or more, then we have an E. coli present result. So this would be an example of the E. coli test. And I would say this is the comparer and this is the sample. So that to me looks like it's E. coli absent. So after the lab looks at the bottles, it's going to issue a report, and it'll tell you either present or absent for both total coliform and E. coli. Well, you've collected your routine samples for the month. What if your routine sample results are TC and or EC present? Well, now you're going to have to collect 3 repeat samples for each positive routine sample within 24 hours of being notified. These samples have to be collected at the location the original sample was taken, at an upstream location within 5 service connections, and at a downstream location within 5 service connections. You're also going to have to collect those triggered source samples we talked about earlier required under the groundwater rule. And if you've had an E. coli hit, you're going to have to issue a boil water advisory within 24 hours of receiving the lab results. If the results of your repeat samples all come back absent, then you're good to go. Just collect the regular number of routine samples the following month. If any of your repeats come back present, you may have to conduct a level 1 or level 2 assessment. These assessments help identify and fix problems to prevent future risks. Okay, now let's talk about the disinfectants and disinfection byproducts rule. This is another rule where you have to sample in your distribution system. Which systems have to sample for disinfectants and disinfection byproducts? Our community systems and our non-transient non-community water systems. And only those systems that add a disinfectant to the drinking water during any part of the treatment process. So why do we add disinfectants to our water? Well, because they inactivate microorganisms, including those pathogenic microorganisms we just talked about. This is a graph that shows the rate of typhoid fever in the United States per 100,000 people over time. The rates used to be high, but as you can see, our large cities began disinfecting with chlorination just after the turn of the century. And as a result, we stopped experiencing typhoid fever in the United States. So that's why disinfection is great. But they also react with naturally occurring substances in the water, and they can form harmful disinfection byproducts. Both disinfectants and DBPs produce negative health effects when present in excessive levels. So disinfectant health effects. You've got acute health effects, eye and nose irritation, other short-term health effects like stomach upset. So if you have too much chlorine in your water, you're going to see things like this. Anemia is also a potential health effect, but this is a chronic effect due to long-term exposure. When we look at the health effects of disinfection byproducts, we see liver and kidney issues, central nervous system issues, anemia, reproductive problems, cancer. These are all chronic health effects. So it's a delicate balance. We're risking microbial contamination versus disinfectants and disinfection byproduct formation. The solution to that risk is to control the health risks from both microbial pathogens and disinfectants and their byproducts. The type of disinfectants that we use to get rid of microbial contamination, chlorine dioxide, chloramine, bromine, and ozone. So these are our chemical disinfectants. UV light is also used in drinking water and wastewater. This is a physical disinfectant, and it doesn't leave a residual in the water. Chlorine is the most widely used chemical disinfectant in the United States. Let's look at how DBPs are formed. So you have that precursor in your water, that naturally occurring organic matter. Surface water systems have more of this than our groundwater systems because they've got like leaves and sticks and fish, and so they're more prone to DBPs. Then we've got our disinfectants. So when we add our disinfectants to the water like chlorine, they're going to combine with the precursors to form disinfection byproducts. Higher DBP formation is going to occur in the warmer months because the reaction happens faster. That's why for most of our systems, your sampling plan is going to have you sampling at very specific months, usually during the summer, like July or August or September, when you've had historically high DBPs in your distribution. So we want to make sure that we have enough disinfectant in our system that it kills the pathogens, but not so much that it makes people sick. The disinfection left in the system after it reacts with everything else in the water is called the residual disinfectant level. It can be expressed as total chlorine residual or free chlorine residual, which are both available for disinfection. The DBP rule specifies a maximum residual disinfectant level. That's the maximum amount of disinfectant that you could have in your water. For chlorine, that MRDL is 4 milligrams per liter or 4 parts per million. And it's calculated based on a running annual average of all of your RTCR monthly samples. So when you take those monthly RTCR samples, you're going to record those chlorine residuals on those chains of custody. Those are reported to EPA, and every month they're going to take all of those samples measured in the past 12 months, add up the residuals together, and divide by the total number of samples to get the running annual average. So if you have one time where you slightly exceed the MRDL, you should still be in compliance because it's an average. Minimum residual disinfectant levels. As we said, you want enough disinfectant in the water that it can kill the pathogens throughout your distribution system. So if you're a groundwater system, EPA recommends a minimum residual in distribution of 0.2 milligrams per liter. You should have at least 0.2 milligrams per liter throughout your entire distribution system, but you can set specific goals for your system. If you're a surface water system, on the other hand, it's a regulatory requirement to have a minimum of 0.2 milligrams per liter throughout your distribution system. And if you ever drop below that, it's going to be a violation, and you're going to have to let EPA know and your consumers know. These are the MCLs for DBPs. If you're disinfecting with chlorine or chloramines, the trihalomethane or THM MCL is 0.08 milligrams per liter. Haloacetic acid is 0.06 milligrams per liter. Chloride is 1 milligram per liter, and bromate is 0.01 milligrams per liter. Monitoring requirements, the number of samples and sampling frequency are dependent on the number of people you serve and your water source type. And as I mentioned, you'll be told which month or months you have to sample based on when your system has had historically high levels of DBPs. Okay, our final distribution rule is the lead and copper rule. Which systems have to sample for lead and copper? Community and non-transient, non-community systems. Okay, the original lead and copper rule was implemented in 1991. In 2001, the lead and copper rule revisions came out. Some of the major provisions include the lead service line inventory, which required public water systems to identify and publicly share locations of lead service lines by October 16th, 2024, the date that still lives in dread in our hearts. And it expanded lead testing in schools and daycare centers, and it requires faster public alerts within 24 hours for high levels. The lead and copper rule improvements, LCRI, came out last year. Some major provisions include the goal of 100% lead service pipe replacement within 10 years, and it expanded testing requirements for schools and child care facilities. The purpose of the lead and copper rule is to protect public health by minimizing lead and copper levels in our drinking water. These lead and copper concentrations primarily come from corrosive water that leaches these contaminants out of our plumbing material. It can come from our service lines, which is why we all had to do the lead service line inventory last year. It can also come from the fixtures, the valves, the internal plumbing of your home, faucets, angle stops, and solder. Lead really affects children, which is why we have seen the improvements to the lead and copper rule focus around testing around schools and daycare facilities. So it can cause all sorts of physical and developmental problems. In adults, it can cause kidney problems and high blood pressure. These are all chronic health effects. Copper causes GI distress, which is an acute health effect, as well as liver and kidney damage and Wilkinson's disease, which are all chronic health effects. Monitoring schedules for lead and copper can be really complicated. The number of samples you have to collect is based on the size of your population, but it's also based on whether you're on a standard or reduced monitoring schedule. So systems on reduced schedules are also required to collect their samples between June 1st and September 30th, because these are our warmest months when the water is most corrosive. Where do we sample for lead and copper? Well, first, we're going to choose sample sites that are most susceptible to lead and copper contamination. Homes, schools, places where water is delivered with lead service lines or that use copper plumbing and lead solder. We sample at consumer taps. So you want to take samples at kitchen sinks. You can take them in break rooms if it's a non-transient, non-community water system, or you could take them at bathroom sinks, but we really prefer locations that are going to be where people are in contact with water most of the time, where they're going to be cooking with it or drinking it. So we prefer kitchen sinks and break room sinks over bathrooms. You don't want to sample at entry point locations. You also don't want to sample at locations that are inactive, such as schools that are closed for summer break or abandoned homes. And you want these samples to be first draw after a 6 to 12 hour hold time. So we want that water to sit in the plumbing for a while so we can tell if it's corrosive. We've been talking a lot about MCLs for the other rules, and MCLs are, again, legally enforceable limits. But with lead and copper, we don't have MCLs. We have action levels, or ALs. So an action level is a trigger for further action. Remember, the goal for lead is 0. But if you have lead above 0.015 milligrams per liter or copper above 1.3 milligrams per liter, you have to take action to make sure that your water is less corrosive. These action levels are based on 90th percentiles. And this can be confusing because what it means is that 90% of your samples should be less than the action level. If more than 10% of your samples are higher than the action level, then you have an action level exceedance. So let's run through a quick example of how to determine a 90th percentile value. Let's say, to make things simple, that your system has to collect 10 lead samples. These are the 10 homes in your system that are most likely to have lead in their water, like homes with lead pipes or older plumbing. So here is a list of our lead results. Well, we can see we have one sample that is 0.022 milligrams per liter, which is over the action level. Remember, the action level for lead is 0.015 milligrams per liter. So is this considered an exceedance? Well, maybe, but maybe not. Here's how we make that determination. The first thing we're going to do is reorder our results. We're going to take those original lead results and we're going to reorder them from the lowest value to the highest value so that the lowest value is on the bottom and the highest value is on the top. So in this case, our non-detect is at the bottom and our highest value, that 0.022 milligrams per liter, is on the top. Now we're going to number our samples starting with our lowest value to our highest. So our non-detect is number 1, and then we're going to number them 2, 3, 4, 5, 6, 7, 8, 9, 10 at our highest value. Now we determine which sample value is our 90th percentile value. The equation for this is the number of samples times 0.9. So we collected 10 samples, so 10 times 0.9 is 9. This means that the 9th highest sample is our 90th percentile value. If you collect 20 samples, you're going to be looking at your 18th highest sample. If you collect 5 samples, an odd number, you have to take the average of the 4th sample and the 5th sample results. So our 9th highest sample value is 0.006 milligrams per liter, which is below the action level of 0.015 milligrams per liter. So even though there is a value that's higher than that action level, this is not considered an exceedance. Well, now what? If you have no exceedance, you have to let each of your sample sites know the lead and copper results, whether there was an action level exceedance or not. Let's say your 9th percentile value or your 90th percentile value was above the action level. What happens next? Well, then we have an action level exceedance, whether it's for lead and copper. We have to do a number of different things. One, we have to monitor our source water for lead and copper to make sure that lead and copper isn't coming from our water source. We have to do water quality parameter monitoring at our entry points and distribution system to determine how corrosive our water is at those points. We have to do public education by distributing information to our consumers about how they can protect themselves from lead and copper. We have to determine our optimal corrosion control treatment. So how can we make our water less corrosive? It may be that we add a corrosion inhibitor or drop our alkalinity. Maybe we have to drop our pH or increase our pH. We have to provide EPA with a report on what our optimal global control treatment is after an exceedance. We may have to do lead service line replacement, or we may have to do under the sink fixture replacement to drop our action levels back below. Okay, so this was the last of our distribution rules. The Safe Drinking Water Act also requires you to communicate with your consumers. It's up to you, the water utility, to communicate with your consumers as part of the public notification rule. You have to communicate to your consumers if there is anything found in their water that poses a health risk. There are 3 tiers of public notifications. Tier 1 notices are the most severe, and they indicate immediate health risk. These public notices have to be issued within 24 hours. Examples are boil water advisories for E. coli presence, nitrate exceedances, and lead exceedances. Tier 2 notices are moderately severe and indicate potential health risks. These public notices have to be issued within 30 days. Examples include other MCLs not immediately affecting public health and failure to address deficiencies. Tier 3 notices are important but not severe, so there's no immediate health risk. Public notice must be issued within 1 year, and examples include administrative issues and monitoring and reporting violations. The other type of consumer communication that you have to do if you're a community water system is your annual consumer confidence report. So every year by July 1st, you have to let your community know what's in their water, the results of the sampling conducted in the past year, and if their system received any violations. Okay, the last thing we're going to touch on real quickly is the record keeping rule. So this rule is in place to ensure transparency by making sure that records are available to regulators and to the public. These records include water quality tests and monitoring reports, or monitoring results, mandates, including compliance reports, public notifications, violations, corrective actions, and consumer confidence reports, and other records such as the lead service line inventories that we did, treatment processes, and your operator certifications. These records must be kept at or near utility offices. The different rules under SDWA require different retention times. A good rule of thumb is to keep documents per SDWA requirements for as long as they're needed. So in the case of public notices and CCRs, you're going to want to hold onto them for at least 3 years. Bacteriological and turbidity sample results, 5 years. Sanitary survey reports, 10 years. Your ChemRad and DBP analyses, 10 years. And your lead and copper results, you want to keep those for 12 years. All right, so just to summarize SDWA, it establishes federal standards for safe levels of contaminants in public drinking water systems. It includes measures to safeguard groundwater and surface water from contamination. It requires systems to monitor, test, and report water quality to authorities and to the public. And I hope that you all take time to look over the Safe Drinking Water Act. So reading and trying to interpret regulations can be pretty confusing. So if you ever want any help trying to understand them, or if you have any questions, feel free to reach out to me or any of us here at the Southwest EFC.